We will now solve problems using the concepts we developed in the last lesson. A cell of EMF 1.5 volt and internal resistance 0.4 ohm is connected to a flash lamp bulb of resistance 1.5 ohm. You can see we are using a flash lamp bulb as an external resistor. What is the current through the filament? Now, if you remember, we had developed equations for external circuit, internal circuit, and the whole internal plus external. Do you remember those equations we developed? The equation for the external circuit is V equal to IR, that is the external. E minus V equal to I times small r is the internal. And if you add the two, E equal to I times R plus R is the total circuit. So you have the external circuit, internal circuit, and the whole circuit. Which of these equations will you be able to use here? We know the EMF, we know the external resistance, and we know the, we know the internal resistance. Well, we know EMF, we know internal resistance, then we know the external resistance. We need to find the current I. So obviously it is the entire circuit, internal plus external, that we're going to use here. Okay, so EMF equal to 1.5 volt, internal resistance R equal to 0.4 ohm, external resistance is 1.5 ohm, and we use the equation E equal to I times R plus R. That will be 1.5 equal to I times 1.5 plus 0.4, and solving that give me I equal to 0.79 ampere. Okay, another one. When a cell of EMF 2 volts is connected across an external resistance of R equal to 2 ohm, a current 0.625 ampere flows in the circuit. What is the internal resistance of the cell? Well, look at the problem and sort of figure out what you can do. We need to find the internal resistance of the cell. Well, we have developed a formula for it. For that, we need the EMF. We have the EMF. We need the potential difference across the external resistor. It's called the terminal potential difference. Well, we know the external resistor. We know the current in the external resistor. Can you use those values to find the potential difference? Yes. And those are the only quantities that we need. Alright, so here we have an external resistor 2 ohm and an internal resistance of 0.4 ohm. The EMF E equal to 2 volt. The external resistance is 2 ohm. And the current in the external resistance is 0.625 ampere. We first find the terminal voltage. That means the potential difference across the 2 ohm as V equal to Ri. We know R, we know I. That will be 2 ohm times 0.625. That is 1.25 volt. That is the terminal voltage across the resistor. We now know the EMF. We know the terminal voltage. We know the external resistor. We can now use the formula we developed for the internal resistance. Do you remember that formula? R equal to, lowercase r equal to uppercase R times E over V minus 1. Maybe R. Now the lost volt. Now I'm doing this to introduce that new concept. What is the lost volt? Lost volt is the voltage used in driving current internally through the cell. So if you now use that concept, you don't even need to use the formula for the internal resistance. The lost volt is the voltage used to drive the same current through the internal resistance R. So that will be 2 minus 1.25, 0.75 volt. Now this is the voltage used for driving current in the internal resistance. So now we can use the internal circuit to solve this problem. The lost volt is a measure of the voltage across the internal resistance. The current through the internal resistor is the same as the current in the circuit, which is 0.625 ampere. So using the internal circuit formula, what is the internal circuit formula? E minus V equal to I times small r. We know E, we know V, we know I, therefore we can find R, and therefore R equal to 1.2 ohm. You can get the same result by going through the formula for the internal resistance that we derived. Let's now talk about energy in an electrical circuit. Well, of course, the electric current flows in a circuit because energy is provided by the cell or the battery. And when the current flows in the circuit, energy is expended in the circuit. Alright, let's develop the concept of energy in an electrical circuit. A current in a circuit is caused by the motion of free charges due to the force they experience in the electric field that exists inside the conductor. Now, what is responsible for that electric field? Well, the electric field is produced by the potential difference between the two ends of that conductor. Thus, work is done by the electric field in driving charges around the circuit. If you now consider a conductor like this, electric charges are made to move inside the conductor due to the potential difference between the ends of the conductor. What is the definition of potential difference? Potential difference is a measure of work done per unit charge. If I say the potential difference between the ends of this conductor is 1 volt, what does that mean? It means to move 1 coulomb of charge from one end to the other, the work done is 1 joule. That is the meaning. So, work done by the electric field in driving charges, work is done in driving charges in an electrical circuit. This work done appears in the form of energy in the electrical circuit. So, energy in the electrical circuit is a measure of the work done in driving electric charges around the circuit. This energy might appear in the form of heat, light, motion, or any other form. We use electricity to produce many different kinds of energy that we require in our life. Is that right? Now, I am able to communicate to you because I am using electricity to produce sound, light, and many other forms. In other words, electricity is doing work for me. I am using energy from electrical circuits. Tell me, what is the definition of potential difference between the ends of the conductor? I want you to understand that very well. Potential difference between the ends of a conductor is a measure of the work done per unit charge that is transported across the conductor. If I say the potential difference is 5 volt, it means for every coulomb of charge that is moved from one end to the other, the work done is 5 joules. That is the meaning. Okay, if the potential difference between the ends of a conductor is 1 volt, it means 1 joule of work is done for every coulomb of charge that is moved from one end of the conductor to the other. Now here I have a conductor that has a potential difference of 1 volt between its ends. It means 1 joule of work is done for every coulomb of charge that is moved from one point to the other. That is the meaning that the potential difference is 1 volt. Alright, let's consider a conductor carrying a current I when the potential difference across its ends is V volt. Alright, we have a conductor here. The current in it is I. What is the meaning of that? The current is I. What is the definition of current? Current is the rate of flow of charge. So when we say the current is I, it means the amount of charge that passes through the conductor per second. In 1 second, there is I coulombs of charge going through the conductor. I ampere is I coulombs per second. Alright? And the potential difference is V volt, means for each coulomb that passed from one end to the other, the work done is V joules. That's the meaning there. The current is I ampere means that I coulombs of charge cross any section of the conductor in 1 second. And potential difference is V means that for each coulomb of charge that move from one end to the other, the work done is V joules. Alright? For each coulomb, the work done is V joules. Now, how many coulombs are passing through the conductor in 1 second? I coulombs. Therefore, what is the total work done in 1 second? The work done per unit charge is V joules. There are I coulombs. Therefore, the total work done will be V times I, so many joules in 1 second. Let's write that down. What is the total work done in 1 second when I coulomb of charge pass through the conductor? For 1 coulomb of charge passing through the conductor, the work done is V joules. Therefore, if I coulombs of charge pass through the conductor, the work done will be I times V joules. And this is the work done in 1 second. And what do you call work done in 1 second? So we say work done is I times V joules, and this is the work done in 1 second. Work done in 1 second is a measure of the power. Is that right? This is a measure of the energy converted from electrical to other forms in 1 second. Therefore, this is called the power in the electrical circuit. Work done in 1 second is what we call the power. So what is the equation for power in an electrical circuit? Power in an electrical circuit is I times V joules per second. What do you call that? Joules per second is a watt. So power P equal to I times V, and the unit of power is the watt, joules per second. Okay. If the current flows for T seconds, look at this. This is the amount of work done in an electrical circuit in 1 second, V times I. If the current flows for T seconds, What is the total energy in the electrical circuit? This is the energy that is converted from electrical to other forms in 1 second. Therefore, in t seconds, the total energy will be VIT. That will be, if I write V using Ohm's law, V equal to RI. So that will be RI times IT equal to RI squared T. When a current I flows through a resistance R for a time T, the energy used up in the resistor is RI squared T. And when a current flows through a resistor, the energy used up becomes heat energy. Is that right? Yes? You see, energy is needed to drive current in an through a resistor because there is resistance for the flow of current. If there is no resistance, then there is no need for any energy spent. So energy spent in driving a current I through a resistor R is RI squared T, where T is the time during which the current flows. And I can also write it as V squared over RT. How did I do that? I can write I. Look at this equation. Energy equal to VIT. Use Ohm's law to write I as V over R. So that will be V times V over R becomes V squared over R times T. So look at the three forms of the energy equation. The energy in an electrical circuit when current flows for a time T seconds is VIT. It is the same as RI squared T. It is the same as V squared over RT. Three different forms of the same equation. Heat generated in an electrical circuit when a current I flows in a resistor R for T seconds. In a resistor, all this energy becomes heat. So heat generated, Q, we generally call the quantity of heat. Q equal to RI squared T. Now, we all pay for electricity consumption, don't we? Why? Because we are using electrical energy. We are consuming electrical energy. We use electrical energy to cook our food, to warm our water, to run our air conditioners, to run our televisions and computers, to iron our clothes. Well, the list goes on and on. We consume electrical energy and we pay for it. Electricity consumption is measured in a unit called kilowatt-hour. It is called one commercial unit and you pay for that. Do you know how much you pay for 1 unit of electricity? Well, if you don't know, ask your parents. They might know. Well, okay, I'm going to leave it for you. Now, what is 1 kilowatt-hour? How much energy is 1 kilowatt-hour? 1 kilowatt-hour, which is 1 unit of electricity, is a measure of the amount of energy consumed at the rate of 1000 joules per second. 1000 joules per second is a kilowatt. Now, if you use energy at this rate for 1 hour, that is a measure of 1 unit of electricity. For example, suppose you have a bulb rated 1 kilowatt. What does that mean, a bulb rated 1 kilowatt? Well, normally we have bulbs rated 40 or, is that right, 40 or 60 watt. What is the power rating of this bulb? This says 40 watt. What does it mean? It means when you connect this to the power supply, it will use up energy at the rate of 40 joules a second. Suppose you have a bulb that is rated 1000 watt. 1000 watt is a kilowatt. Now that bulb will use up energy at the rate of 1000 joules every second. Now, you turn that bulb on for 1 hour. The bulb is using energy at the rate of 1000 joules per second for 1 hour. And that amount of energy used by the bulb for 1 hour is what we call 1 commercial unit of electricity. And you know, you pay for that much of electricity about 10 cents. And that much is called a kilowatt hour. That is, 1 kilowatt used for 1 hour is a kilowatt hour. So can you tell me, how would you calculate the number of units? Tell me, if you have a water heater that is rated at 2 kilowatt, that means that water heater will use 2000 joules of energy in 1 second. Alright? If you have that 2 kilowatt water heater, if you turn it on for 2 hours, how many kilowatt hour do you actually use? All you need to do is multiply the power in kilowatt by the time in hour. So 2 kilowatt multiplied by 2 hours is 4 kilowatt hour. You will consume 4 units of electricity. So 1 kilowatt hour is energy used at the rate of 1000 joules per second for 1 hour. 1 hour is 3600 seconds. And that is 3.6 times 10 to the power 5 joules. This much of energy is what is called a kilowatt hour. And it is very easy to calculate the number of kilowatt hours. All you need to do is multiply the power in kilowatt by the time in hour. That will give you kilowatt hour as we normally read it. For example, a 100-watt bulb burning for 5 hours. How many kilowatt hour is the power it consumes? First of all, write the power in kilowatt. 100 watt is 0.1 kilowatt. Multiply that with the time in hour, and that will be 0.5 kilowatt hour. So a 100-watt bulb burning for 5 hours consumes half a unit of electricity. Let's do an example. What is the current in the filament of a 60-watt bulb when connected to a 110-volt supply? Well, we know the power. The power of the bulb is 60 watt. What is the equation for power? Well, power is 60 watt and the voltage is 110 volt. Do you remember the equation we developed for the power? Power is V times I. Don't forget that. V times I. And we know the power, we know the voltage, therefore we need to find the current. What is the current? I equal to P over V. That will be 60 watt divided by 110 volts. That is 0.55 ampere. Another problem. What is the cost of operating a 500 watt electric heater for 20 hours if electricity cost 8 cents a unit? Well, first of all, you need to figure out the number of kilowatt hours. The power given is 500 watt. write it in kilowatt. That is 0.5 kilowatt. And how many hours is it used? For 20 hours. Therefore, how many kilowatt hour are consumed in here? The number of units equal to power used in kilowatt multiplied by the time in hour. So that will be 0.5 kilowatt multiplied by 20 hour, that is 10 kilowatt hour. And this is what we call one commercial unit. And each unit costs 8 cents a unit. It now costs about 10 cents a unit. So the cost is number of kilowatt hour multiplied by the cost per unit. That will be $0.8 is the cost of using that equipment for about 20 hours. Next example. A 10-volt battery is connected to a 120 ohm resistor. Calculate the power delivered to the resistor. Well, you know the power equal to VI. You can also write it in terms of RI squared or V squared over R in many forms. So we have V equal to 10 volts and the resistance R equal to 120 ohm. We need to find the power V. V power equal to P equal to V times I. But we don't have I. What do we do now? Well, I can write I as V over R. Is that right? Use Ohm's law to rewrite your I equal to V over R. That means the power now equal to V squared over R. Now that will be 10 squared over 120. That is 0.83 watt. Another example. Batteries are rated in terms of ampere-hours. For example, a battery that can supply a current at the rate of 5 ampere for 10 hours is rated 50 ampere-hour. When you go buy a battery for your car, actually the batteries are rated in ampere-hours. Do you know how much is the capacity of the battery that you use in your car? How many ampere-hours? Well, normally a car battery is about 60 ampere-hour. It means your car battery can supply current at the rate of 1 ampere for 60 hours or at the rate of 2 amperes for 30 hours or at the rate of 20 amperes for 3 hours and so on. Now remember, when you start your car, the starting coil will take a large amount of current, but for a very short time. Okay. Now, what is the total energy in kilowatt hours stored in a 12-volt battery rated at 60 ampere-hour? At the rate of $0.08 per kilowatt hour, what is the value of the electricity produced by this battery? Well, the battery is rated 60 ampere-hour means that if the battery supplies a current I ampere for T hours, then I times T equal to 60 ampere-hour. Ampere-hour. I ampere times T hours. You see, 3 ampere times 20 hours is 60 ampere-hour, right? Okay, so I current in ampere multiplied by the time in hours is 60 ampere-hour. And energy equal to VIT. We have been using this equation. Power is V times I multiplied by the time will be the total energy delivered during that time T. Therefore, energy equal to VIT and IT equal to 60 ampere hour. So the total energy the battery will supply will be 12 volts times 60 ampere hour. That will be 720 watt hour. In other words, you can see, use the unit correctly. 12 volt times 60 ampere hour will be 720 watt hour. And that will be 0.72 kilowatt hour. You see that? Watt hour becomes kilowatt hour by dividing by 1000. And a kilowatt hour is a commercial unit. Now, the value of the electricity therefore is 0.72 multiplied by 0.08. That is 0.058 or 5.8 cents. That means each time that battery is fully charged, it will contain electricity worth about 5.8 cents. But remember, your car battery is continuously being charged and recharged. So during the lifetime of the battery, you will be storing hundreds of times worth this electricity in your battery. Let's do another problem. A 15 watt electric heater is used to heat 100 grams of water in a beaker. If 75% of the heat generated is used for heating water, how long will it take for the water temperature to change from 20 degrees Celsius to 35 degrees Celsius? Well, here we have heat generated electrically, and that heat is used to heat up water. That means we are going to use two principles. The amount of heat generated by an electric heater is RI squared T or VIT, any of the equations. And the amount of heat used by water to increase its temperature is mass times specific heat times change in temperature. You forgot that equation? We are now going to combine these two. Okay, let's pick our data. The power is 15 watt. That is the power of the heater. It means the heater will produce 15 joules of energy per second. The mass of water you want to heat is 0.1 kilogram. Initial temperature of water is 20 degrees Celsius. Final temperature of water is 35 degrees Celsius. And we want to find the time taken for water to increase its temperature from 20 degrees to 35 degrees. So let's start by saying let T be the time taken for the temperature to increase from 20 degrees to 35 degrees. Alright, if T is the time taken, what is the amount of energy used during that time? What is the amount of energy produced during that time? How much energy is produced in 1 second? 15 joules. Therefore, how much energy will be produced in T seconds? The quantity of heat generated is Q equal to VIT, or simply power multiplied by time. VI is the power. So that will be power multiplied by the time. The power means the energy per second. You multiply that with the time during which the appliance is used, you get the total quantity of heat produced during that time. That will be 15 watt times t seconds, that will be 15 t seconds. Now, not all this energy is used by water. Only 75% of this is used by water. So what is the amount of heat actually used by water? Is 75% of this quantity. The amount of heat used in raising the temperature of water is 0.75 times 15T. 75% of 15T. That will be 11.25 T. This is the quantity of heat produced by the heater and delivered to water. And this amount of heat is used by water to increase its temperature. That means the amount of heat used by water to increase its temperature is mass times specific heat times change in temperature. Alright, what is the specific heat of water? You remember that one? It's 4,180 joules per kilogram per Kelvin. So this 11.25 T must be equal to mass times specific heat times change in temperature. Alright? If C is the specific heat capacity of water, the amount of heat required to raise the temperature of m kilogram of water from theta 1 degree Celsius to theta 2 degrees Celsius is mc delta theta, mc times change in temperature. We know the mass, we know specific heat of water, we know the change in temperature. So the mass is 0.1 kilogram, specific heat is 4,180 joules per kilogram per Kelvin. The change in temperature is 35 minus 20, and that will be 6,270 joules. Now I have colored these two quantities similarly. That means this quantity of heat produced and supplied by the heater equal to this quantity that is used by water. So 11.5 T equal to 6,270, therefore T equal to 545 seconds, that is 9.1 minutes. A typical kind of problems, you must know how to solve these kind of problems. Okay, well, this has been a good 3-part lesson. I want you to review all the concepts we have developed. We developed the concept of electric current, electric power, and how to use the concept of Ohm's law and all these to solve problems. The internal energy of a cell. So please review all these and make sure that you can do all such problems. And I will get back to you with the next lesson a little later.